the largest and the smallest value of star of 6 ones. So there doesn't exist a binary operation star on Z satisfying these three criteria. What will remain after the 49th turn? Welcome to my channel Beneath to Zenith. Myself Obhijit, and I create contents on various topics of higher mathematics and upload in this channel. For now, the concerned topic is group theory from abstract algebra. In the previous video, I briefed the history of group theory, and the link of that video can be found in the I-bar. Today, I will begin group theory formally. Well, group theory is an algebraic system consisting of a pair of a non-empty set and a function satisfying certain conditions. In the context of group theory, these functions are what we called binary operations or binary compositions. We will see them explicitly now. Let us start with the definition of binary operation. So, given a non-empty set A any function f from A Cartesian product A to A is called a binary operation on A. Okay, we usually denote f of a comma b by some other symbol. F of a comma b by a composition b or by s star b or by some other symbols. Okay, let's look at some examples. Clearly, the usual addition is a binary operation on the set of positive integers or natural numbers. Obviously, if we add two positive integers, again we will get a positive integer. Similar thing happens for integers as well. If we add two integers, then again we will get an integer. Similar for rationals, if we add two rationals, again we will get a rational number. Real numbers, same thing. So it's a binary operation on n, z, q and r. However, this usual addition is not a binary operation on the set of irrationals. For example, if we take any irrational number, its negative is again an irrational number. But what happens if we add them? We'll get 0, which is a rational number. So, sum of two irrationals may not be a irrational again, and therefore it is not a binary operation. So, for example, we can take square root of 2 plus negative of that is 0, which doesn't lie in r minus q. So, addition is not a binary operation in r minus q. Another example, if you take subtraction is a binary operation on integers. Obviously, if we subtract one integer from another one, we'll get an integer again. However, subtraction is not a binary operation on the set of positive integers. If we subtract a larger integer, larger natural number from a smaller one, we will get a negative integer, which is not a natural number. But subtraction is not a binary operation on the set of positive integers. For example, 1 minus 2, which is minus 1, that doesn't belong to n. Alright, now we have a definition. So this pair A composition, A comma composition, we give a name. So if composition is a binary operation on A, we call this algebraic system, A composition, a groupoid. So we have seen some examples of groupoid here. For example, n comma plus is a groupoid, z comma plus is a groupoid, q comma plus is a groupoid. But n comma subtraction minus is not a groupoid because subtraction is not a binary operation. Well, in the next problem, you might check your observation power. The problem is the following. In a groupoid, A composition, if X composition, Y composition X equals Y for all xy in A, then show that X composition Y composition X equals Y for all xy in A. Pause and think about it. You will find it interesting. Okay, so let us try to solve it now. So what is given us? What is given to us? Given is this equality. So given equals y for all xy in A. And what to show? We have to show this. And if we look at this given thing and what to show, there is only one change, that the change of position of this parenthesis. Here this parenthesis is towards the end and here it is at the beginning. Okay. But we cannot really change the parenthesis with only this groupoid property. Just with this binary operation we cannot change it. So we have to do something. Well, first of all, what happens if we interchange x and y? Let's see. So let's denote this by star. Now we interchange x and y, will obtain so x will become y and y will become x. So y compose x compose y equals y becomes x for all xy. Let's denote it by double star. Okay. Now let us see carefully. We have to bring this parenthesis for the first two pair. So what we can do? Okay, so what happens if we replace x by this entire thing? Let's see. This is the only possible thing we can do. Let's do it. So replace x by this entire thing, x compose y in star. So replace x by x compose y so as to obtain so we'll replace x by x compose y. So what will have? X compose y compose y compose x compose y equals to y. Now from double star we already have this value equals to x. So just replace this by x. So by double star which is the desired expression, x compose y in parenthesis and composition x equals y, and this holds for all xy in A. Okay. Now we'll see some few more essential definitions. Next definition is the definition of commutative property. So what is that? So a binary operation composition on A is said to be commutative if A composition B equals B composition A holds for all AB in A. So examples: clearly the usual addition is commutative on set, because if you add two integers in any order you're going to get the same integer, right? So addition is commutative on set. Whereas subtraction is not commutative on set. For example, 1 minus 2 and 2 minus 1 are not certainly same things. So, but subtraction is not. Next definition is a very strong property of a binary operation, which we call associative property. So what is that? A binary composition binary operation composition on A is said to be associative if A composition B composition C equals A composition B composition C for all ABC belongs to A. Okay. So again, this addition is associative on Z. You can easily check it. Addition is associative on Z. However, subtraction is not. For example, if you take all ABC to be 1, what happens in the context of left hand side? So 1 minus 1 minus 1, that is 1 minus 0, which is 1, and from in the context of right hand side, this becomes 1 minus 1 minus 1, that is 0 minus 1, which is minus 1. So this is the definition of associative property, and some examples you have. Now it is a very strong property. Why? So one of the perspective is that we can define this composition unambiguously due to this associative property. Well, what does it mean? That means one can compute this composition in this way, like A composition, B composition, C composition, D, and one might prefer it to calculate in this way as well. Okay, but these two are going to be the same element in this set A. Okay, so let me show how we can equate them using this associative property. So let's start with this. So what we have, this equals to here this thing you can think about a single element, let's say A. So A compose C compose D. So isn't it of this form? Yes, it is of this form. So this will become the left hand side of this equality, that is A compose B compose C compose D. So we can define composition of any finite number of elements, finitely many elements, unambiguously. That is one of the advantage of this associative property. And due to this, we can define any integral, any positive integer power of an element of this set. We can define for any element A in A, we can define A to the power n to be composition of A n times. Because this composition of A n times, it is now well defined. Whichever way you put the parenthesis, we are going to get the same value. So basically, associative property allow us to think an expression regardless of the parenthesis. Okay. So this holds for all n belongs to n. And when we study groups, we'll see this exponent can be extended to all integers, including 0 and all negatives also we can think about. All right. So here you can see addition is both associative and commutative on Z, and subtraction is neither commutative nor associative on Z. So let me ask you one question. Can you think about a binary operation on R, the set of real numbers, which is commutative but not associative? Another one, can you think about a binary operation on a real number set which is associative but not commutative? Okay, let's think about it. Now we can have a definition. If a binary operation on A is associative, then we call this algebraic system a composition a semigroup. So Z plus is a semigroup, but Z minus is not. Okay. Again, you might check your observation power through this following problem. So the problem is the following. In a semigroup, a composition, if A composition B equals C composition A, then B equals C. Show that this composition is commutative. Again, pause and think about it. So here is sort of cross cancellation is happening, isn't it? A is left here, A is on the right here, and we are cancelling it to get this. Then using this, we have to show that this operation is commutative. Okay. So how can we solve it? So what is our target? Our target is to prove this equality. So we fix some as two elements arbitrarily. So fix A and B from the set A. Now it is a semigroup. That means associative property is there. So let's make use of it. So by associative property, what do we have? This equals, right? Okay. Now you think this entire this composition to be your B and this composition to be your C, and if we compare with the hypothesis, so it is of the form A compose B equals C compose A, and assumption tells us that this would imply this B and this C are equal. So this implies B compose A equals A compose B, and this is what we are looking for, and therefore A becomes composition becomes commutative, and because A and B are arbitrary, so this holds for all A B in the set A. All right. Okay. Now let me share a few more interesting problems with you. So the next problem is the following. Show that there does not exist a binary operation star on Z satisfying number 1, star is anti-commutative, what is the definition of anti-commutative? That is A star B equals negative of B star A for all A B in Z. Number 2, star is associative, and number 3, for each A in A, there exist B and C in Z such that A equals B star C. Okay. So there doesn't exist a binary operation star on Z satisfying these three criteria. So we can prove it by contradiction. So let's try to solve it. So if possible, let there exist a star satisfying all three. So if possible, let there exist star satisfying one, two, and three. Okay. Now we fix a non-zero integer. So choose R belongs to Z and R is non-zero. Okay. Now if we apply 3, then R can be broken in two pieces, like let's say A and D. So by 3 there exists elements A and D in Z such that R becomes A star D. Again we apply 3 on D. By 3 there exists elements B and C in Z such that D becomes B star C. Now just replace D by this expression to obtain, then R becomes A star within parenthesis B star C. Okay. All right. Now what if we apply this anti-commutativeness? So this implies, so by anti-commutative property, that is by 1, so if we switch this and A, then we'll get negative of this, that is minus of R equals B star C star A. All right. Now by associative property, this becomes B star C star A. So this equality holds by property 2. Okay. Now again we repeat this anti-commutative property. So if we apply this 1 again, then this minus R becomes plus R, and then these two elements will switch their position. So that is C star A star B. All right. Now again by associative property, this becomes C star A star B. Okay, so this is property 2. Okay, now again we apply anti-commutative property. So this R will become minus R equals this, and this will interchange their position, A star B star C. And by associative property, this is same as A star B star C. So by 2. But this is where we started from. and this is equal to r. So this equals r. So minus r equals r. That means 2r equals 0. This would mean r equal to 0, which contradicts that r is non-zero. And why this contradiction arises? Because we assume something impossible, that is, there does not exist star binary operation star on Z satisfying 1, 2 and 3. Okay. Alright. Now we'll see another problem which you might apply for any recreational purpose. Let me show this problem. So our next problem is the following. So we are given this set S equals to 1 half, 1/3 till 1 by 50. And at each turn you choose two elements x and y arbitrarily, randomly from this list of elements, and remove x and y, those chosen elements, and replace them by this expression x plus y plus xy. Then the question is that what will remain after the 49th turn? Okay. Alright, so let's try to understand this problem. So after first turn, how many elements will be here? So initially we have 50 elements. So after first turn, so you are removing 2 and replacing them by 1. That means you are getting 1 less element than this. So you have 49 elements after first turn. Then again after second turn, you will get again 1 less element, that is 48. So likewise after 49th term, only 1 element will be left out. Okay, this element may not be from this list, okay, but exactly 1 element will be left out. So and we are asked to find what is the number. All right. So at first one should be concerned that will it depend on the choice of elements, but actually not. It doesn't depend on the choice of elements. We'll see this in the spirit of this binary operation. Okay. Let us do one thing. So we are removing x and y by this, removing x and y and replacing them by this value. So let's call this replacement operation, let's denote it by star. So let's say you are replacing x and y by this x star y. So that is your x plus y plus xy, right? All right. Now you can see this star is not a binary operation on S, on this ambient set S, because what happens if we apply star on 1 and half? So 1 and half means 1 star half will give us 1 plus half, that is 1 plus 1, which is 2, but 2 doesn't belong to this set S. So star is not really a binary operation on S, but star is a binary operation on any ring containing S. Well, why I am saying ring? Because it involves, this expression involves two operations, addition and multiplication. So for example, we can take just simply the rational numbers. So we can define a binary operation star on Q. So define binary operation star on Q by this. So let me rewrite this. So by x star y equals x plus y plus xy. Okay, now what we can do, we can adjust slightly xy plus 1 minus 1, and then if you take x common from here and here, you'll get 1 plus y and 1 plus y, so it will become x plus 1 into y plus 1 minus 1. All right. Now it is quite clear that it is commutative, right? So clearly star is commutative on Q. We can show that star is associative as well. So to see this, we pick three elements x, y and z in Q. So what is that? X compose x star, y star z. This becomes y star z means this expression. So this is y plus 1 times z plus 1 minus 1. Again we apply this same thing, x plus 1 into this plus 1. So this is x plus 1 minus 1 plus 1 will get cancelled and we'll have z plus 1 and then this minus 1. Okay, now we can see this expression is symmetric around x and z. That means if we interchange the position of x and z, we will get the same expression. That means if we would have started with z star, y star, x, we would have reached the same expression. So since this is symmetric in x and z, this is same as z star, y star, x. Since x plus 1, y plus 1, z plus 1 is symmetric in x and z. Now we can apply this commutative nature, commutative property of star. So we can switch around this star and this will become this. Now we can switch around this star, then this will become x star y star z. So we can conclude that star is associative on Q. Thus star associative on Q. So commutative and associative. All right. Now come back to the problem again. So here we have 50 elements and after 49th turn, I hope you to convince yourself that when we are applying 49th turn, we are basically replacing each one of them. Each one of the elements we are replacing. You can look at some smaller value and you can check this. So which I mean, so the final after 49th turn, okay, let us give some name to this. So let xi equals 1 upon I for I equals 1 to 50. All right. So after 49th turn, we have some expression of this form x sigma 1 star x sigma 50, where sigma is some bijection of these elements 1 to 350, where sigma is a bijection from let's give it injective. So for sigma is some bijection. So sigma depends on your choice of elements while removing elements. Okay. But okay, now one thing. So what associativity actually allow us to think this expression irrespective of the parenthesis. Okay. So we don't have to think about the parentheses. Whichever order we calculate, we are going to get the same element. And this commutative property will allow us to rearrange them in usual order. Like, so by this is same as x1 star x50. Okay. Now what is x1 star x50? Okay. Now you look, what is that expression? So when we consider this star between two elements, we are getting this x plus 1 into y plus 1 minus 1. While we are considering this star between three elements, x star, y star, z, we are getting this expression. So when we are considering this star between 50 elements, so we are supposed to get x1 plus 1 till x50 plus 1 minus 1. Now what is, so in a compact form, short notation, it is xi plus 1, I runs from 1 to 50 minus 1. And if we put the value of xi, which is 1 upon I, it becomes I plus 1 upon I minus 1. Now if we put the value here, it becomes I equals 1 will give us 2 by 1, then 3 by 2, final value is 50, so 51 by 50 minus 1, right? Okay, so this is telescoping product, so there are some certain cancellations like this. So it becomes 51 by 1, that is 51 minus 1, which is 50. So this is the number which will remain after 49th term. Okay. Well, before I conclude today's session, I would like to give you a question to solve. Okay, so this problem is for you to solve. So the question is the following. We define a binary operation star on the set of all positive real numbers by this formula: a star b equals a by a plus b, and this is indeed a binary operation on positive reals. Then you have to find the largest and the smallest value of star of 6 ones. Okay, this star is not associative. That's why you can find multiple values for this expression, and we can check it that it is not actually associative, because what is the value of this? 1 star 1 star 1, so it will give us 1 star and then a by a plus b, so 1 by 2, again 1 by 1 plus half, that is 3 upon 2, so it is 2 by 3. Whereas this 1 star 1 equals 1 upon 2 star 1 a by a plus b, so 1 by 2 upon 3 upon 2, which is 1 upon 3. These two are different value, so these two are different. So this star is not associative. Okay. So multiple values are possible for this due to various choice of parentheses. So in the next video, I'll solve this problem. Meanwhile, if you could solve, let me know in a comment. Thank you for watching this video, and with this, let me conclude today's session. Thank you once again.